Hey everybody, it's Mr. Morris. Today we're going to talk a little bit about net ionic equations, which is the last part of our chemical equations and reactions unit. Net ionic equations are a way to represent double replacement reactions without having to show everything that's going on. All they show are the ions that are actually involved to produce the solid precipitate. Scientists don't care about the other parts, the kind of what they call spectator ions, which are the ions that never leave solution. So the first thing we need to do is talk just a little bit about the fact that this equation right here represents a double replacement reaction. Both of my reactants were aqueous ionic compounds, which means more or less that we took them and dissolved them in water. So remember, when that happens, what we get are some potassium ions and some sulfate ions that are floating around as individual ions and not actually hooked together. So when I make an aqueous solution by taking usually some kind of solid powder and dissolving it in water, the dissolving process causes the K2SO4 to what we say dissociate. And dissociate means to break apart. So the K2SO4 compound dissociates or breaks apart into the potassium ions and the sulfate ions that make it up. So right now they're just floating around in that solution. That's also true for our other reactant, the calcium chloride. And when I mix both together, we all of a sudden have a lot of ions floating around in water, some that are more reactive than others, some that would rather be hooked together and form a solid compound as opposed to staying as individual ions. And that's what makes a double replacement reaction actually happen. So what we can see from this equation up here is that when I mix everything together, the calcium and the sulfate would rather come together to form a solid precipitate, kind of a little chunky, flaky piece you'd see floating in that water, as opposed to being ions by themselves. Which means that everybody else is a spectator ion that's just floating around, and we don't care so much about those. Scientists really only care about the ions that we used to make that solid precipitate. So I've already given you the chemical equation for this double replacement reaction. So what we need to do now is figure out what ions we have, what are spectator ions, what ions are important to get our net ionic equation. So something we can do here is first things first, write what's called the complete, if I can spell, ionic equation. So let's move this guy over just a little bit and write each ion that we have in this equation. So let me grab my pen here, and here we go. So I take the subscript for individual elements, and I say that I have 2 potassium ions with a 1 plus charge. I then say that I have 1 sulfate ion with a 2 minus charge. And I continue now to my next compound, and I say that I also have 1, it's a plus sign right there, 1 calcium ion with a 2 plus charge. And I'll have 2 chlorine ions with a 1 minus charge. And that gets me through my reactants. I'm kind of starting to run out of space here. I'm going to do the same thing for my products and see what we have. So in this case, pick a different color. Because of this coefficient of 2, what I'm going to find out is that I have 2 potassium ions with a 1 plus charge and 2 chlorine ions with a 1 minus charge. And then the last thing is this guy right here, the CaSO4 solid. Because it became a compound and it's not individual ions floating around in solution, I don't break it apart into the ions that make it up. I simply leave it as CaSO4 solid. Everybody else there is aqueous, and I can add that little symbol to every single one of these ions to show that it is dissolved in water. I'm going to skip the rest of that part for now, and we'll add them back in before we get finished. So now that we have our complete ionic equation, I want to use that to write the net ionic equation. So down here, we're going to get our net ionic equation. And what I do is I get rid of the spectator ions. Anything that looks exactly the same on both sides of the arrow, I can get rid of and cross out. So let me get a different color here. So let's see, 2 potassium 1 plus ion on the reactant side, 2 potassium 1 plus ion on the product side. And because that spectator ion doesn't change, I simply cross it out and can get rid of it. Come to the next guy, SO4 2 minus on the reactant side. However, when I come to the product side, it doesn't look the same. We don't have an SO4 2 minus ion anymore. It's become part of the compound. So I actually need to save this guy and use him later on. Same thing with the calcium. I have a calcium 2 plus ion on the reactant side. However, he's part of a compound on the product side, so it doesn't look the same, so I can't cross him out. So I'll save him for later. And then the last thing, I have 2 chlorine 1 minus ions on the reactant side and 2 on the product side. They look exactly the same, and I can cross them out. And so now all I'm left with are the 3 parts circled in green. So my net ionic equation simply shows the ions that it took to mix together to make our solid precipitate compound in this chemical reaction. So my net ionic equation would be, I need 1 SO4 2 minus ion, which is aqueous. To that I'm going to add 1 calcium 2 plus ion, which is aqueous. And that's going to produce 1 calcium sulfate compound that is solid. And right there is my net ionic equation. It just shows the ions that were involved that actually made the solid precipitate, which is the calcium sulfate. If I don't include the ones, because again, it's just understood to be 1 if they're not there, that's totally okay. If you want to put them, that's fine as well. But notice that I have all the parts that I need. I have aqueous ions on the reactant side going together to make 1 solid precipitate ionic compound on the product side. The only other thing to notice is that even though I wrote the sulfate first and the calcium second, you always write the metal or the positive ion first and the negative ion second when I make an ionic compound.